For this calculation, we're going to need to know the mean titra. You have your table here, which is a little bit misleading, but we'll get to that in a second. So, you've got experiment 1, experiment 2, and experiment 3. You've filled out all the other information. We know that's going to be the same, the volume of HCl. Now, the volume of sodium hydroxide used, which is the endpoint, and the titra, in this instance, are the same thing. I think they've made some sort of mistake around this title here, but that's fine anyway. So the value in each of these is going to be the same. These two, and these two. Okay, so to calculate your mean titra, you're going to take the first titra, which is over here. So you can write here, down the bottom, mean titra equals, it's going to be this first value here, 22.00 cm cubed, plus the second titra, 26.00 cm cubed, and that's going to be plus the third titra. It should all really be on one line, but I can't fit it on, so it's going to be plus that one, 24.00 cm cubed, put a bracket around that. And it's all going to be divided by the number of titras you have. In this case we have 1, 2, 3. It's going to be divided by 3. And that's going to give the answer, therefore, mean titra equals 24.00 cm cubed. Now, you have to know here that cm cubed is the same as a milliliter. Okay, so 1 cm cubed equals 1 milliliter. The reason we are using cm cubed is because concentration, which we're going to work out, is measured in dm cubed. Okay, so it just makes it easier at the end, otherwise you have to do some calculations. Okay, so now you've got your mean titra, which is, in this instance, 24, which is just all your titras added up, divided by the number of titras there. Make sure you use this 2 decimal places at the end, because that's what it asks for. So it will be 0.05 or 0.00 possibly, because of the degree of accuracy. Okay, now when you have your mean titra, which is 24 in this instance, you need to write out the balanced equation, but we know our equation is balanced anyway, so we're a step ahead of the game. So that would be HCl plus NaOH NaCl plus H2O. Okay. Now, we know that we have a volume of HCl, which is, put it in blue, which is 25.0 cm cubed, because that's how much we were told to use. So 25 milliliters, so 25 cm cubed, because they're the same. And that concentration is 0.5. You could put 00 after it. It would be the same number, but because I believe, without checking, that's what we were told, that's the degree of accuracy we have to use. And that's measured in moles per dm cubed. I will do another video on why that little cube's got a minus in front of it at some point, but don't worry too much about that for now. Okay, so we know that how much sodium hydroxide we used, because that's our mean titrate. Okay, our mean titrate is how much we used of sodium hydroxide. So we can write that in there, 24.00 cm cubed. Okay, and we know, because this equation is balanced, that one mole of hydrochloric acid reacts with 1 mole of NaOH. But by convention we don't write the ones in, that's why they're not there. Because that's nice and easy for us. So now we know the volume here and the concentration there of hydrochloric acid. So the number of moles of hydrochloric acid will be number of moles of HCl equals concentration times multiplied by volume in cm cubed. Okay, now what we've got here is cm cubed, so we really want it in decimeters cubed. So all we do for that, draw a line, and we put divided by 1000, we'll give the answer in decimeters. Now that equals it's going to equalise the concentration. That's the concentration of hydrochloric acid, because we're dealing with hydrochloric acid here, and we know that is 0.5 moles. So that's going to be 0.5, the concentration of hydrochloric acid, multiplied by the volume. And we know the volume we used because that was given to us, which is here. So that's 25.0 cm cubed. And that's all going to be divided. Put some brackets around it because that's the correct thing to do. We always calculate anything inside the brackets first, so it just makes it easier to follow, really. So 0.5 times 25, and we know that's going to be equal to, in yellow, equal to 0.0125. And don't forget to put what it is afterwards, so that's moles. It often happens that people don't put the moles or the whatever you're measuring afterwards, but make sure you always write at the end what it's measuring. So that's 0.0125. So now you know that 1 mole of hydrochloric acid neutralizes 1 mole of sodium hydroxide, because that's this bit here. So 1 and 1, because they're in the ratio of 1 to 1, because it doesn't say otherwise, and it's a balanced equation. So 0.0125 moles of hydrochloric acid, which is our answer, just try a different colour here, must neutralise 0.0125 moles of sodium hydroxide. Because if 1 mole up here neutralises 1 mole here, then it's the same ratio. So the same number, you could put 500 HCl, it's still going to be 500 NaOH. So the number stays the same for each one in front. They follow each other. So we now know how to calculate the concentration of NaOH, which is what we are trying to achieve. Put a question mark there. So we can rearrange this formula here for number of moles, but you don't really need to, because it's a nice simple. I'll show you how to do that in a minute. So the concentration of NaOH equals moles of NaOH times 1000 over, where are we? So we put a bracket around that. Over volume in centimetres cubed, or cubic centimetres. And that equals, so the moles of NaOH is going to be the same as the moles of what we found out here, which we know is going to be 0.0125, and that's going to be time multiplied by 1000 as per the calculation here, and that's all going to be over the volume of cm cubed, cubic centimetres of NaOH, because we're dealing with NaOH there. So that's going to be over 24.00 cm cubed. We've got the times 1000 here because it converts it into the correct unit of measurement for concentration. But you could quite as easily not. You could just put 0. You could put Well, we'll leave that for a second, but just put times 1000 there. It'll just make it easier, and it will save a step in the calculation, which makes it a bit better for you. So that is going to equal 12.5 over, which is all that part there. Got the eraser out. This part here. So that's going to be 0.0125 times 1000 is going to be 12.5, and that's going to be over 24.00, and that's going to equal 0.52, and because that's a concentration, that's going to be measured in moles. If I were to write it, moles per dm cubed. Make sure then you can put something at the end, which is green, that says therefore the concentration of NaOH required to neutralize however much of HCl. You can put quantities in there, I'm just doing it rough. Therefore, the concentration of NaOH required to neutralize however much of hydrochloric acid, as per what the question asks you, you have to check what the question's asking you, equals 0.52 mole per dm cubed. Make sure you put the mole per decimeter cubed at the end, 0.52. If you didn't do the times 1000, you would have 0.0125 divided by 24. So you would have, and I am referring to, there we go, I'm referring to this bit up here. So I'll write it over here in red. You would have 0.0125, because the formula is concentration of NaOH equals moles of NaOH over volume, but we just put the extra 1000 in there. But if you didn't, you'd have this number here divided by 24.00 cm cubed, and that would equal 0.0005, which equals 5.20833 times 10 to the minus 4 in scientific notation. So you're going to be creating a little bit of a problem for yourself, because of course what you would do is, once you've got this answer here, you could theoretically times that by 1000, but it will give you a slightly less accurate answer because it's already rounded and taken off the 0.2 part. The 2 part there. See, because you lost the 2. There's no 2 there now. So you want to be avoiding, that's called a rounding error really, and you really want to be avoiding that. It's not good. And that is it's quite simple to do, but you just have to know what the conventions. Oh, by the way, this will be equal to 0.5, and you see 0.5 here. I'll give you 0.5 if you did it that way, and we have 0.52 here, which is more accurate. Okay, so it's a more accurate answer. And if you've done lots of these types of calculations up here with timesing it by 1000 afterwards, throughout the course of your calculation, the rounding errors will build up and it can give you quite a way out answer. Yeah, so just be careful of that. And degrees of accuracy, I'll look at the question again and do something on that tomorrow, I believe. And that's what to give your answer. Make sure you always give your answer, this one here, the final answer, to the number of decimal places that's asked for in the question, if it asks. If it doesn't, you're always going to go for, I'll do another video on this, but you can see from this top, you have 25.0, which is, what is a different colour? 25.0 here, and 0.5 there, and 24.00 there. Okay, so the number of decimal places just means how many figures after the decimal place there. On the first two here, you've only got 1, but on this one over here, you've got 2. So your answer, final, will not be 0.52. It will actually be 0.5. But for our purposes here, we're not taking this into consideration, I believe, so it will be 0.52 because it's more accurate. But the degree of accuracy up here, 25.0 and 0.5, that shows, see, it could be any number because of rounding. So 25.0 could in fact be 25.0, 25.01, 25.02, 25.03, 25.04, and that's it. See, because I'd round it back if they were giving it in what, if they wanted 25.00. So if they wanted to give, if they were rounding it, sort of the degree of accuracy of the measuring devices they use usually. So the measuring, like the cylinders, you can't actually get the exact, very, very precise reading. It's only between 2, so a reading of 25.0 over this side could be any one of these, but we don't know which one. So that is why on our final answer we use a degree of accuracy of only 1, because obviously these will change the calculation if it's any one of those. So you only give the degree of accuracy at the end to the lowest number of degree of certainty you've got here. So it's only 1 decimal place, but we won't be doing that, I think, on this course. So just go for what it asks for. Okay, and that is how you calculate, and our question marks there, so we can just write in our answer, which is 0.52 for this purpose, 0.52, and always moles per dm cubed. And always do the, unless it asks for a different measurement of volume. But concentration is measured in dm cubed anyway, so you've got to remember that. Don't give the concentration in cm cubed unless it specifically asks for it. So you always have to convert it. And I hope that helps and explains a little bit. It's a bit dry and it's a bit boring, but once you get the hang of these things. Oh, and I will show you one other thing which will help you greatly with these concentration calculations, which is, if you, some of you may be familiar with this, but if I create a new page after, right, if you draw a triangle, I'm not sure how to do it on here, but maybe that one. Okay, so we'll do it in yellow. Triangle. Okay. So we've got 3 sections of the triangle. You've got moles. Drawing you up. Moles at the top. You've got concentration here, and you've got volume, which is measured dm cubed. Okay, so you put a multiplication here. Okay, and that gives you so moles. What this means, you put the write the top one first, so moles is at the top of the triangle. It doesn't really want to write moles, so we've written that one first, and then you put equals, and then it tells you what it equals. It equals concentration by volume. Concentration by volume. Nice and easy. But if you want to find any of these other variables, what you do, and this line here, I'm drawing now, that means it's a division. So you can, I'm not sure how to do this. So if you choose any one of these you want to count, we just worked out what moles is. That's easy. You write the top one and then you write the other two. But if you wanted to work out the volume, for example, okay, you'd write volume because that's what you want to calculate. So you don't need to worry about that anymore. So you can cover that volume up with your hand or just pretend it's not there. So volume isn't there anymore, so you've just got these two. Well, you know, it's moles divided by concentration, because moles is at the top, concentration's at the bottom, and this blue line in between is a division, and volume's gone, so it's the only thing it can be. So volume equals moles over concentration. Likewise, if you wanted to calculate concentration, you would write concentration. And we don't need concentration anymore because we just finished writing it. So I've just covered it up with my hand pretty much. So you're only left with moles on top of volume. So it must be equals moles on top of volume. So it's quite easy to use these triangles. Moles at the top equals they're next to each other, so they're multiplied. And if moles is at the top, it's just moles divided by something. So moles divided by that one, or moles divided by that one, depending on which one you want to calculate. These triangles work for a few different equations, but not all, so don't think you're going to be using it for all equations. But they are useful when they do work, if you need to rearrange an equation. But I'll do a little video on rearranging an equation. It's really simple. It's quite easy once you get the hang of it, and you really need to know it because you can start working other things out quite quickly then. Okay, and that will that's all you need to know really about this, I believe. I will put some notes about tomorrow, maybe about what to put in each section. But that's the mathematics part taken care of. Just work through it, follow the examples I gave, and input your own numbers in place of the ones I used, and it should be a piece of cake.